So now we come to one of the most important parts of the proof, and that's introducing the loops. So I want to be able to work out when an element in the matrix is large and when it is not. And recall that the elements of the matrix, so they're determined by this P sigma P tau elements, where these things are actually given by products. So it's product in M, product in J, PM, T, star. So for the matrix element to be large, I need that all of the individual factors in the product is large. And so that's what I'm going to be using to introduce the idea of loops. So recall I have a dichotomy. I have that either PM sigma J is related to the value, say the Q, the other value, tau mj. Okay, so this was P related to Q for our general definition of the simultaneous saturation system, or this thing decays. Now, if I have too many terms that are decaying, the full product of them is going to be small. So what I want to do is I want to avoid decay. And I want to see what that forces for me. So I'm going to start at m is equal to 1, and I'm going to start at this P1 sigma 1 of j. And to avoid decay, I require it to be linked up by condition 1 to P1 tau 1 of j. Okay, otherwise, that part of the product will be 0, will be decaying as r lambda. So now I use the fact that the m index only acts as tagging. So this thing is actually equal to P2 tau 1 of j. Okay, the points are the same if their j index is the same, independent of what the m tag is. But then I could just rewrite that as tau 2 inverse tau 1 of j. So just using group properties of the permutations there. And the advantage of that is I come back to my matrix and I say, well, all right, that means that I must be able to connect up this thing to now P2 sigma 2 tau 2 inverse tau 1 of j. Otherwise, I would have a factor that decays. Okay, so now I've included condition 1 and condition 2. But I can keep going. Okay, so this is equal to P3 sigma 3 inverse sigma 2 tau 2 inverse tau 1 of j. Okay, so now I connect that one through by C3. Okay, so now this comes over to the tau side, and I look at this and I go, all right, that's P3, tau 3, sigma 3 inverse sigma 2, tau 2 inverse tau 1, j. Okay, so now I'm picking up this sort of pattern as I move through my loop. If I go for one more, P4, so I have tau 4 inverse 2, tau 2 inverse tau 1 of j. Come back via C4 to P4, sigma 4 of J. Okay, so as I move around the loop, I build up a way of addressing. Now, say M was equal to 4, so I've got 4 different operators in my simultaneous saturation system. If I want it to be a loop, well, these two things have to be equal to each other. So that would give me that sigma 1 of J is equal to this address. Tau 3, tau 1, J. Or to express it in terms of the identity, this thing. And so this is what I call my loop condition. It does matter a bit whether you're in an even or odd case. So you see in the paper, I divided into even and odd. I treat the even case first, and then we can just treat the odd case by embedding it into a higher dimensional even setting. So this is the loop condition, and these are the things that I want to be appearing in my trace. Okay, so my trace should contain all of the elements P sigma, P tau that obey this looping condition. And for those ones, those are the ones that I'm going to be able to draw a diagram between their elements. And so that's how I'm going to be able to relate my question about the diagram into my estimates in terms of the trace bound. So there's a couple of things that are important to notice here. So the first one is that exactly what the address is doesn't depend specifically on the permutations itself, but on what I'm calling the transitions. So sigma 1 inverse and sigma 4, and then I have sigma 3 inverse and sigma 2. So if I had 2 different sigma, but they obeyed the same transitions, then if one of them has the addressing property with respect to a particular tau, the other one has the addressing property with respect to that tau as well. And that's also true for the taus. Okay, so you've got to pair tau 4 inverse with tau 3 and tau 2 inverse with tau 1. And this is why I wanted things to be even in terms of the loop condition. The odd loop condition doesn't have this nice breaking into transitions. The other thing that's important is I could have obviously started with P1 tau 1 of J as my starting point for my loop and gone this way. Okay. And in the paper, I refer to these as weavings. You can kind of see why when you draw them live. So you're weaving back and forth between the P sigma and P tau entry of the matrix. So in terms of going back in the other direction, that's basically like taking the Hermitian conjugate of the matrix. So this is why we required some symmetry. So we are going to need our condition to be symmetric so that we can weave in either direction. And so that feeds into one of the conditions that we had about the simultaneous saturation. So what we want to do is we want to construct another matrix, an averaging matrix A, where if I multiply my averaging matrix A, so I have my energy matrix W, I'm going to define M is equal to averaging matrix times energy matrix. averaging. And the averaging operator A is going to define specifically so that elements that appear on the diagonal of M are precisely those that obey the looping condition. And so this really drives the trace bounds. And we will then be comparing the one eigenvalue we have to a sum over loops. However, we know that everything except for the trivial loop must collapse. And so that's why this averaging and the weaving through the entries of the matrix is so very important.